Hi everyone, this is Mrs. G.A. and today we're going to talk about exponential growth and decay, and we're going to do this with the context of separable differential equations. Alright, I have a warm-up for you guys to try, so please pause the video and give it a shot. Alright, go ahead and check your work here. So we're going to separate our variables, and then on the right it's just 3/4 dx. Then we're going to integrate, giving us this. And then we could use this point that we know our function passes through to help us find c, which ends up being the natural log of 4. So then from here, all we need to do is try to isolate y. So I'm going to rewrite it in exponential form, e to this power equals absolute value of y. This we can rewrite as e to the 3/4 x times e to the natural log of 4. This will simplify to 4. This can stay as is, and this term will always be positive, so we can lose our absolute value signs. All right, so today we're going to be working with exponential models, and we're going to actually create the exponential models ourselves by solving a separable differential equation. So for these types of problems, we're going to start with a scenario that's really common for certain quantities in nature, like radioactive material or bacteria, which grow or decay at a rate that's proportional to the amount of substance present. So that means, for instance, if maybe something that has more of a substance will grow or decay faster, and maybe if something has less of a substance, it will grow and decay slower. So it's saying that the rate of change is not constant, it's proportional to the amount of material. So typically we'll start with something like this. So dy dt equals ky. So you could see that this means the rate of change of y with respect to t is equal to k times y. So k is a constant, but it's proportional to the amount of y. So again, it's not just a constant, it depends on this y amount. So if we start with this and we treat it as a separable differential equation, kind of like in the warm-up, let's see what happens. So I'm going to divide both sides by y, so I have 1 over y dy equals k dt. And then we'll integrate both sides. And this gives us the natural log of absolute value of y equals kt and then plus c. And then here we will want to solve for y, so we'll rewrite it in exponential form. So e to the power of kt plus c. So let's keep simplifying from here. So I will rewrite this as the absolute value of y equals e to the power of c times e to the power of kt. And now from here, we're going to consider a really common scenario with these types of problems. Let's say that the initial condition is given, which means that we know the amount when time equals 0. So let's say when t equals 0, we have y is equal to, I'll say y naught. So this is a really common way to denote the initial amount. So if I substitute this into my equation, we have y naught, which would be right here, equals e to the c times e to the power of k times 0. Because again, we're looking at the initial amount, and that will be when time is equal to 0. Anything to the power of 0 is 1, so we can see that e to the power of c, which is just a constant, right, because c is a constant, e is a constant, so that constant is equal to y naught, which is essentially just the initial amount. So if I substitute that back in to our equation, we can say that y equals y naught times e to the power of kt. And you'll notice that this is our exponential model. This should look really familiar for exponential growth. So we have initial amount times e to the power of kt T, where K is some constant of proportionality. Oh, and then I forgot to mention this, the reason why we dropped our absolute values here is because both of these terms are always going to be positive. So here you can see that by starting with this relationship, the rate of change of that is directly proportional to an amount, and rewriting it as a separable equation and solving for y, we actually were able to derive our exponential growth model or decay model. All right, so each of these that we do today, we're not just going to use our general formula for growth or decay, we're actually going to derive it completely from the beginning using a separable differential equation. So this says a freshly inoculated bacterial culture of strep A contains 100 cells. So that's our initial amount, 100 cells. When the culture is checked 60 minutes later, it is determined that there are 450 cells present. So assuming that the growth of bacteria is proportional, the growth of bacteria is proportional to the number of bacteria present, we're going to find a general equation for the number of cells present at any time t measured in minutes. So when it says the growth of bacteria, we can write this, we could say dB dt is proportional, so we can give that k, that constant of proportionality, to the number of bacteria present, which would be our output, which we could call b. So we're kind of treating this like a y value. So we're starting with this, and then just like we did on the last slide, we're going to treat it as a separable differential equation. So we have 1 over b dB equals k dt. We'll integrate both sides. So the natural log of the absolute value of b equals kt plus c. And this b value here is going to be, it represents the number of bacteria. So this would never be negative. So we don't need to worry about the absolute value sign anymore. So now we still want to solve for b. So we have our equation. So I'm going to rewrite it in exponential form. So we get b equals e to the power of kt plus c, which, as we've done a couple times now, if we rewrite it like this, it allows us to solve more using our initial conditions. So we're told in the problem that when time is 0, so when it started, when it was, it says freshly inoculated, which implies that that's the starting time. The number of cells, which is b, was 100. So we're going to substitute those values in. So 100 equals e to the c times e to the power of k times 0, which is just 1. So we see e to the power of c equals 100. And again, this is just a constant. So this constant is equal to 100. So if I go back here and substitute that in, we have b equals 100 times e to the power of kt. Now here, you'll notice that we still have this k value, which we need to find. So we're going to use that second piece of information that tells us when time equals 60, when t equals 60, the number of bacteria is 450. So now I can substitute that in. So I see 450 equals 100 times e to the power of 60 k. So we have k times our t value, which in this case is 60. Then we could try to solve for k. So 4.5 equals e to the power of 60k. And so I'm going to need to rewrite this in logarithmic form. So 60k equals the natural log of 4.5. So we have k equals 1/60th times the natural log of 4.5. So that's our k value. So if I go to plug that back in here, so I'm going to take this and substitute it right here. And then we'll try to simplify. There's a couple different forms we can write our final answer in. So if we have b equals 100 times e to the power of 1/60th natural log of 4.5 times t, if we are using our calculator, we can actually just plug this in to our calculator, and get a decimal approximation for this value, and it ends up being 100 times e to the power of, so that value is just 0.0251 t. So this is one way we could create our model. So this is with a calculator to help us simplify this value. But if we weren't using a calculator to do a decimal approximation, we can still simplify it a little bit more. So we have 100. If you have e to the power of natural log of 4.5, this part will just reduce down to 4.5, but the 1/60t would still be in our exponent, so 4.5 to the power of t over 60. So this would be without a calculator. So now that we know our models, again, this is without a calculator. Now that we know our models, we can now answer other questions about this scenario. So they're wondering how many cells were present after 15 minutes. So we could use either model. We'll do it with both. So we would do B of 15. So we could do 100 times 4.5 to the power of 15 over 60, which we'd still need our calculator to help us get this decimal approximation. So 145.648 bacteria, or if we plugged it into our other formula, we would have 100 times e to the power of 0.0251 times 15, which is approximately 145.718 bacteria. So either way, I would say 145 bacteria, right? Because you can't have a decimal of bacteria. That wouldn't make sense. And we wouldn't want to round up, because then we're saying that that next bacteria already exists when it doesn't quite exist yet. So for this one, even though technically math would tell us to round up, logic would tell us to round down. Now let's look at this last part. Here they're asking how long would it take for this culture to double. So now we're actually going to solve for t. So if the amount is doubling, the initial amount was 100, so that means our new amount would be 200, so equals 100 times 4.5 to the power of t over 60. So to solve this one, we're going to want to rewrite it in logarithmic form. So t over 60 equals log base 4.5 of 2. So we can multiply by 60 and then get a decimal approximation for this in our calculator. If your calculator can only do common logs and natural logs, we'll have to use a change of base formula. So log of 2 over log of 4.5, and we'll get approximately 27.651 minutes. And if we were using our other form, so 200 equals 100 times e to the power of 0.0251 t. Again, we'll still want to rewrite this in logarithmic form, so 0.0251 t, left out a 1 here, equals the natural log of 2. So t is the natural log of 2 all over 0.0251, which is approximately 27.615 minutes. So very, very close, very, very similar answers, regardless of which form of our exponential growth model we are using. All right, let's try another one together. So this one says that bismuth-210 is a radioactive element with a half-life of 5 days. So first we're going to write a general exponential model for this radioactive element for how much is the amount after time in days, given that the rate of decay, so this is important, the rate of decay is directly proportional to the amount of element that is present. So for that last statement, the rate of decay, we can call it D, I'll say B for bismuth, dt. So that's the rate that it's changing. And it says is directly proportional to the amount. So it's K times the amount, which is B. So now we'll treat this as a separable differential equation. So 1 over B dB equals K dt. We'll integrate. And we get the natural log. Here we know that B stands for the amount of this element that's left, so that amount will always be positive. You can have a negative amount, so we don't need to worry about the absolute value sign for this one. Equals KT plus C. And then we will want to solve for B, so we'll rewrite in exponential form, e to the power of KT plus C, and then we can split this up into two portions. So e to the power of C times e to the power of KT. So kind of similar to what we did last time. If we're saying the initial amount, if we want to define it as B naught, that would be when time equals 0. So we can say B naught equals e to the power of C times e to the power of K times 0. This is 1. So this constant, remember, e to the power of C is just a constant. E to the C equals B naught at the initial amount. So we can make that substitution for E of C. So this constant I'm just going to replace with B naught. So here's the start of our model, e to the power of KT. So here we have two variables that we don't know. It's okay to have B and T, but B naught, again, just represents the initial amount. We don't have that information yet, so we're just going to leave this as B naught, but understand that it means the initial amount. And then we also need to solve for K. So we can solve for K using this extra piece of information about half-life, which is the number of days it takes for the material to be cut in half. So this is saying, since the half-life is 5 days, it's saying after 5 days, the amount, which is B, is going to be 1/2 of the initial amount. So I could just say is 1/2 B naught. So I'm going to replace B with 1/2 B naught, and then B naught times e to the power of 5K. I replace T with 5. And then from here, we'll just start solving. So I'll divide both sides by that initial amount, B naught. And then I could rewrite in logarithmic form. I'll go back up to the top here. So K is going to be 1/2 natural log, or sorry, 1/5 natural log of 1/2. So now I can substitute that back in. E to the power of 1/5 natural log of 1/2 times T. So this we can simplify a little bit. So we have two options. Without a calculator, we know that e to the power of natural log of 1/2, this portion will simplify to just 1/2. So we could say B equals B naught times 1/2 to the power of, we still have the T times 1/5. So we'll say T over 5. So this is one form of our model. And this would be a no calculator model. But if you wanted to, you could also plug this into your calculator to get a decimal approximation for 1/5 natural log of 1/2. And then you would end up with B naught times e to the power of negative 0.138629 T. So this would be with a calculator. So getting a decimal approximation for 1/5 natural log of 1/2. So either model is fine, it just depends on what you have to work with. All right, let's look at part B. So this says if you had a sample of 800 grams of this element, so that's our starting amount, so B naught, how much would remain? So they're asking us to solve for B after 30 days. So that's going to be our T value. So we could plug this into either formula. So we could say B equals 800, our initial amount, times 1/2 to the power of 30 over 5. So here we get 12.5 grams of bismuth 210. Or if we use our other equation that we generated with our calculator, so 800 times e to the power of negative 0.138629 times 30, we actually get the exact same answer, 12.5 grams. All right, and then for part C, they say, given that you still started with that 800 gram sample, just like from part B, so this is still going to be B naught, when, so when they ask when, they're asking us to solve for T, would there be only 1 gram left? So this would be the amount, so B. For this one, I'll just solve with our no calculator formula. So I'll do 1 equals 800 times 1/2 to the power of T over 5. So here we're going to isolate our exponential term, and then we could rewrite this in logarithmic form. So T over 5 equals log base 1/2 of 1 over 800, and then we'll multiply by 5. And then if we want to get a decimal approximation for this, you may need to use change of base formula for your calculator. So I'll write it as common log of 1 over 800 over common log of 1/2. Then you'll get approximately 48.219 days. All right, so remember when you're doing these types of problems, in this chapter, we cannot jump straight to our exponential growth or decay model that we know. You do need to derive it by starting with a separable differential equation and then solving that and finding the constant. So this is the process I would expect to see on your homework or on a test or quiz. All right, so we're going to do one more type of separable differential equation. So this is called Newton's law of cooling. So according to Newton's law of cooling, the rate of change of temperature of an object is directly proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So if y is the temperature of the object, t is time that it's been cooling, and then capital T sub s we'll call the surrounding temperature, and then K is that constant of proportionality. So this says the rate of change of temperature, so we'll say dy dt, because we're calling temperature y, is, so they're equal, directly proportional, so I'm going to multiply a constant by the difference between, so you see the minus, the object, the temperature of the object, which again was y, and the surrounding temperature, which was T sub s. So this is the start of Newton's law of cooling. So now we're going to have to solve for y, since this is a separable differential equation, to help us actually derive this Newton's law of cooling. So first we're going to separate our terms. Zoom out a little more. So we have 1 over y minus t sub s. Remember, t sub s is just a constant. And then we have, I forgot my dy, equals k dt. Then we can integrate both sides. And that gives us the natural log of the absolute value of y minus t sub s equals kt plus c. And I'll just call this one C1 for now. So from here, let's rewrite this in exponential form. So we know the absolute value of y minus t sub s equals e to the power of kt plus c sub 1. And then we can split up our exponents on the right. And then here we know that e is a constant, c sub 1 is a constant. So I'm just going to replace this entire thing. I'm going to say e to the power of c sub 1. I'll just call it c sub 2. So we'll just replace it with a new constant. And in doing so, c sub 2 is going to take care of the absolute value on the left. So that leaves us with y minus t sub s equals c sub 2 e to the kt. So this kind of takes into account the plus or the minus that's within the absolute value. All right, so from here we're going to, kind of like when we did with our exponential model, I'm going to work up here now. We're going to consider an initial condition. So an initial condition is when t equals 0. And I want to say y is equal to y naught. So I'm just calling y naught the initial temperature. So this represents the initial temperature. And again, if it's the initial temperature, that must occur when time is equal to 0. So I'm just going to replace y with y naught. And I'm going to replace t with 0. So c sub 2 times e to the power of 0, and that allows us to solve for c sub 2. So it's just y naught minus t sub s. So it's the initial temperature minus the surrounding temperature. So I can replace that here. I'm going to substitute for c sub 2 right here. And then I can finish solving for y. I'm also going to add t sub s to the other side. So I end up with y equals t sub s plus y naught minus t sub s times e to the power of kt. So remember, t sub s is just a constant. That's just the surrounding temperature. Y naught is our initial temperature. And k is going to be a constant of proportionality depending on what type of scenario we are working with. And then here, now that we've finished solving for y, I'm just going to use some different variables. Instead of saying y for temperature, I'm going to replace it with t, just t, and then, so instead of saying y naught, I'm going to replace it with t naught. I just used y to make it a little bit easier to work with as we were solving. So t equals t sub s plus t naught minus t sub s to the power of e times e to the power of kt. So this is Newton's law of cooling. And again, we can find the temperature of our object after a given amount of time if we know the surrounding temperature and the initial temperature. So here you can see this is another case where we can use a separable differential equation to help us derive a model or a formula. All right, we're going to try one last example together. So here we have Mrs. G.A.'s cup of coffee was 180 degrees when freshly brewed, but after 2 minutes in a room that is 70 degrees, the coffee is cooled to 165 degrees Fahrenheit. Mrs. J prefers her coffee to be exactly 120 degrees before she drinks it. So first we're going to write a model for the temperature of Mrs. J's coffee at any time using Newton's law of cooling. So for a problem like this, I would give you that statement that we started with. I would tell you that the rate of change of the temperature, so d capital T dt, is equal to, or is directly proportional, so equals k times the difference between the temperature and the surrounding temperature or surrounding material. So I would give you that statement so you can create this initial differential equation. And for this, T is the temperature of the coffee at any given time at T minutes. And then T sub S is that surrounding temp. And we're going to treat that as a constant. So we're going to assume that that is not changing throughout this entire problem. So first we need, we can substitute for T sub S. We can do that. And then we need to separate our differential equation. So I'll say 70. And we're just going to know that it is in degrees. So I'm going to say 1 over T minus 70 dt equals k d lowercase t, and then I can integrate both sides. And that gives us natural log of t minus 70, of absolute value of t minus 70 equals kt plus c1. And then we're going to go through this process again of splitting up, or rewriting in exponential form, and then splitting up our c term, or our e term. So e to the power of c1, which is just a constant, and e to the power of kt. And again, here we're just going to call c2 e to the power of c1, and we're going to encompass that absolute value, the plus or minus from our absolute value. So we can write this as t minus 70 equals c sub 2 times e to the power of kt. Now from here, we can use some information about our initial temperature to help us solve for C sub 2. So we were told in the problem that that initial temperature, so when T equals 0, when the coffee was freshly brewed, it is 180 degrees. So T equals 180 degrees Fahrenheit. So we could substitute that in. And that'll be e to the power of 0, which is just 1. So we see that C sub 2 is equal to 110. So we can substitute that into our equation, and I'm also going to add 70 to the other side. So we have 70 plus 110 times e to the power of kt. But we still need to find that constant of proportionality. So we can use that other piece of information that we were given. We were told that after 2 minutes, so when T equals 2, the temperature of the coffee is 165 degrees Fahrenheit. So we could substitute that information times e to the power of 2k, and we could keep solving from there. And then here we could say 2k equals the natural log of 95 over 110. So k is equal to 1/2 of natural log. If I simplify this, it's 19 over 22. All right, so now that we have our k value, I'm going to go back and substitute it here, and then we could just do a little bit more simplifying to get our model. So we have t equals 70 plus 110 times e to the power of 1/2 natural log of 19 over 22 times t. So we have two options here. One, we could just simplify without a calculator, so we know e to the power of natural log of 19 over 22. This portion just becomes 19 over 22 times 19 over 22 to the power of 1/2 t, so I'll say t over 2. And remember, you cannot multiply these two numbers because of order of operations. So this would be one way to model our temperature. Or we could use our calculator to get a decimal approximation for just this portion right here, which is approximately negative 0.0733. So we could also write a model that looks like this: 110 times e to the power of negative 0.0733 times t. So two different ways that we could write our model. So now that we have our model, we can go and try to answer part B. So we want to find the time at which Mrs. J will start drinking her coffee. And it says in the prompt that Mrs. J prefers her coffee to be exactly 120 degrees. So we want to find lowercase t when uppercase T is 120 degrees. So for this, we could just plug it into our formula. I'm going to use the non-calculator form. I'm going to use this one. So remember, I'm substituting uppercase T with 120. So equals 70 plus 110 times 19 over 22 to the power of T over 2. And then we're solving for T. So we're going to isolate our exponential term. So we end up with 50 over 110 equals 19 over 22 to the power of T over 2. And then we're going to rewrite this in logarithmic form. So it's going to be T over 2 equals log base 19 over 22 of 50 over 110, which is 5 over 11. And then here we can get a decimal approximation for this in our calculator, and we might need, again, to use our change of base formula depending on your calculator. So we could rewrite it as a common log. And this should give us the approximation of 10.756 minutes. Okay, so just remember for these problems, although we know from that last slide what Newton's law of cooling is, we're always going to start with our differential equation using the statement about the proportionality, the constant proportionality, and then we're going to go through the process of actually generating the model ourselves. Okay, so I would expect to see all of this work all the way through, despite the fact that we actually already know what Newton's law of cooling is. All right, so that is all for today's video. Thank you so much for watching.